Hi everyone, I am Alaa Omar, PhD student at the University of Canterbury. I'm going to present our paper here, which is real-time emulation of a modular multi-level converter with battery energy storage system for electric vehicle application. This figure shows the main dedicated electric vehicle blocks or components, which include the inverter and the battery management system and the charger. The modular multi-level converter has been investigated recently to replace the main inverter as a centralized drive, which also replaces the battery management system and the charger. So, the three-phase modular multi-level converter comprises three phases or legs. Each leg has two arms, the upper and the lower arm. Each arm has a number of submodules. The submodule itself has two switches and a battery cell. So instead of the bulk battery in the normal electric vehicles, the battery cell or the battery cells are distributed inside the submodule. The battery cell can be equalized or balanced using the submodule switching process. As example here, let's assume that we have two submodules connected in series. This cell inside submodule 1 can be bypassed by switching the main switch, which is SM1 on, and the auxiliary switch, SX1, will be switched off. If we want to insert the battery, we can switch the auxiliary switch in the submodule number 2 on. When inserting the battery, that means the battery voltage is added to the terminal phase voltage. And this process of insertion and bypassing will lead to a global state of charge equalization inside the converter. There are some chances and challenges to drive the electric vehicle using the modular multi-level converter as follows. The modular multi-level converter can be used to drive the electric vehicle motor, and at the same time, it can be used as a battery management system by insertion or bypassing the submodule batteries, which gives redundancy of the operation of the converter, so that one of the batteries, due to any operational aspect, can be bypassed, such as high temperature. The modular multi-level converter also can be used to charge the batteries from a single-phase source or three-phase source or from a DC source. And the nature of the modular multi-level converter, because it's a multi-level converter, that means high number of levels, there will be reduced switching losses and lower harmonic currents. But there are some challenges of the operation of the converter. Because the converter has high number of submodules and high number of switches that require high number of switches that should be controlled from the control system. Also, the high number of the voltage sensors that will be used to measure the battery's voltage in the start of operation to decide the state of charge or the initial state of charge of the submodule batteries. There are some other operational aspects of the converter operation, such as minimizing the circulating current and balancing the state of charge of the batteries, in addition to the main control function of the controller or the converter to drive the electric vehicle motor. To investigate the operation of the modular multi-level converter in the lab, it requires scaled down prototype. However, in real time, it comprises more than 100 submodules in one arm. So the scaled down prototype in the lab wouldn't reflect the actual operation of the converter. However, it will be a scaled down prototype. So in the next slide, we are going to mention the hardware in the loop and how it can be used to emulate the real-time operation of a full-scale modular multi-level converter. As shown in this figure from IEEE standard for the testing of microgrid controllers, There are many types of testing conditions or testing tools that can be used to test the dynamic performance of electrical systems, such as the simulation. The simulation can be used to cover different operational condition of the electrical system. However, it has a very low fidelity compared to the full system. In between of the simulation and the full system, there is the hardware in the loop. The hardware in the loop can be categorized in two types. First one is the controller hardware in the loop. In the controller hardware in the loop, if we have a controller that is interfaced to an emulation platform, and the emulated platform can process the dynamics of a specific electrical system in real time, that's called controller hardware in the loop. The real-time feature is very important because it can be then extended to implement what is called power hardware in the loop. In the power hardware in the loop, the emulated platform can interface a physical component of the system, such as a motor. In an example, if we have emulated system and a controller, the emulated system will generate a signal, and this signal can be amplified to drive a motor. And then the motor, let's say the motor speed or a feedback from the motor will be an input to the controller. And the controller will be driving the emulated platform to test the operational condition of the motor. So this arrangement is called power hardware in the loop. After the introduction about the modular multi-level converter and the hardware in the loop, we are going to propose a complete model of the converter. The battery model is the first step, as it is the main unit in the converter structure. There are different modeling approaches in the literature to model this battery. One of them is voltage open circuit or open circuit voltage versus the state of charge of the battery. This method utilizes the actual battery performance curves to model the battery. The challenge of this method is to determine the correction factors. The correction factors are two different correction factors, the temperature correction factor and the discharge rate correction factor. The temperature actually affects the operation of the battery and the performance of the battery, because temperatures below 0 Celsius will degrade the battery and will increase the battery internal resistance. This will lead to a decrease in the terminal voltage of the battery. So, in the other side, if the temperature is high, that means the terminal voltage will be higher. But higher temperatures actually will accelerate the aging of some batteries, like a lithium-ion battery, and also might lead to irreversible changes of the battery chemistry. As shown in this figure, the battery current is multiplied by these correction factors from this charge rate and the temperature correction factor. And then the state of charge is calculated using the equation in the at the end of the at the bottom of this slide. Then the state of charge is used to calculate open circuit voltage using the lookup table of the battery curve. Once the open circuit voltage is calculated, another correction factor, which is called temperature correction voltage, will be added to the open circuit voltage. Then this open circuit voltage will be used to calculate the terminal voltage of the battery using the internal resistance of the battery. And then this terminal voltage will be applied to the load, and then the current is the consumption of the load. So these are the curves of the battery that are given by the manufacturer and by and the emulated results of the battery operation. These curves are for discharge rates at nominal battery current and at twice the nominal battery current, which is 2C, and 4C and 6C. Actually, during the discharge test, temperature changes from the start till the end of the battery discharge test. So, in the following hardware in the loop model that has been presented in this paper, the temperature is assumed to be constant. Now, we have developed a battery model. The complete converter model will be calculated. So this is the equivalent circuit of a three-phase modular multi-level converter. And as example, here we have VAU, which is the output voltage of the submodules that are connected in series in the upper arm of phase A. And this actually applies for all arms voltage. To calculate this upper voltage, which is VAU, the switching behavior shall be represented. There are many methods to represent switching action, such as the detailed representation or physical model. The detailed representation actually requires significant modeling time. There is another approach with which is the equivalent arm modeling. This approach is mostly used in the power system because it doesn't show the performance of the battery inside the arm. So we have implemented the ideal switching representation using the state variables of the submodule, which is actually sufficient to represent the battery behavior and the dynamic operation of the converter. So as example here, if we have the auxiliary switch, which is SX, is on, the submodule voltage is the battery voltage. And if this auxiliary switch is turned off, that means the main switch which is SA is on, the submodule voltage will be 0, but the battery voltage will be unchanged. And the battery current will be 0 because there is no current is consumed from the battery. The arm voltage can be expressed using this equation here, the first equation, to include the conduction resistance. Another term utilizing R1, which is the conduction resistance of the switch, can be added to represent the switch voltage drop when conducting in the second equation. There is no DC link here, but the DC current in the bus bars can be represented as the total currents in the upper arm or in the lower arms of the converter. Considering also the VDC of the converter and the inductance of the arm and the resistance of the arm voltage can be represented as shown in these two equations. The DC current value is calculated from the DC voltage of the three legs of the converter, as shown in the equation number 4. Finally, the circulating current, which circulates in the converter legs and arms, is very vital component to determine the converter arm currents, which actually this current originates from the voltage differences between the upper and the lower voltage in one leg and between legs voltages. The circulating current equation is expressed in the last equation in this slide. Now we will present the comparison of the prototype and the held performance. To verify this proposed real-time model, Microlab box from DSpace is used to implement the CHIL, which is the controller hardware in the loop of the converter. Also, a laboratory prototype of 4 levels converter is built, and the main controller is the same Microlab box. to the right of the picture here, we can see that the converter arm arrangement, which comprises 4 submodules. Each submodule has a voltage sensor to measure the open circuit voltage, and the initial state of charge of the submodule battery can be calculated. The converter hardware in the loop and the prototype are tested with static RL load, and the details of this load are shown in the table. In the prototype and hardware in the loop, 2 switching methods are used. The nearest level control method and phase shifted PWM method are used. In the nearest level control method, the duty ratio is 0.8, as shown in the figure to the left. In the sub-figure A, the prototype arm currents and voltages in phase A are shown. Duty ratio is increased from 0.8 to 0.9 to test the dynamic performance of the converter. The hardware in the loop result is shown in the sub-figure B. The figure to the right shows the arm currents and voltages in the phase B of the prototype in the top and the hardware in the loop in the bottom one. This figure shows the arm currents and the voltages in phase C for the prototype as well, and the hardware in the loop using nearest level control switching method. When using the phase shifted PWM, the arm currents in phase A are shown in the left for the prototype and the hardware in the loop as well. So the prototype is shown in sub-figure A and the hardware in the loop is shown in figure B. Similarity of the dynamic performance of prototype and the hardware in the loop is clear here between both of the figures. The arm currents in the phase B are shown in figure A and B to the right of the slide for hardware in the loop and prototype as well. Then again, we can see the arm currents in phase C for the prototype in sub-figure A and for the hardware in the loop for figure B. And this figure shows the phase current in the 3 phases when using the prototype nearest level control operation in sub-figure A, and the 3 phases as well when using the hardware in the loop nearest level control operation in figure B. And the last one, the 3-phase currents in PWM control method in the hardware in the loop operation. The state of charge of the individual batteries in the 6 arms of the converter are compared when using the hardware in the loop in the left of the slide and when using the experimental prototype to the right of the slide. We can see that the state of charge and the performance of the converter is nearly similar in the 2 cases. That means that the operation of the hardware in the loop or real-time emulated system is very close to the experimental prototype. State of charge, as mentioned earlier in this presentation, are equalized using the bypassing and insertion algorithm of the batteries. Finally, the conclusion on the paper. In the conclusion, actually in a conclusion here, we can see that how the complete real-time model of the converter is built and described, starting from the battery up to the complete model of the system. The comparison that we have presented shows that the prototype and the real-time emulation, they are showing similarity in the operation, and the switching representation that we have presented is valid and really is sufficient to model the converter. This representation of the modular multi-level converter with battery energy storage system is a novel representation of the converter and is implemented on FPGA micro lab box from this base. This controller hardware in the loop is not limited to a specific number of elements, and it can be extended and utilized as power hardware in the loop for further investigations of electric vehicle system. Thank you for listening. Appreciate your feedback. Thank you so much.